Let's begin 4.2. It is second derivatives, plural, and graphs. So, for one, we need to talk just even what a second derivative is, and it's really exactly what it sounds like. You take the derivative of the derivative, and then we'll discuss what that means. So I just grabbed this one as a quick, easy example. A polynomial. Let's say we've got f of x equals 2x to the third minus 4x squared plus 5x minus 10. So of course we all know how to take a derivative. And I made some comments about that also, but here f prime of x would equal 6x squared minus 8x plus 5. And we know that a derivative represents a rate of change, and specifically the instantaneous rate of change. When it comes to, the best way to probably describe that as far as like a physical object would be a velocity. So if that first function tells you where an object is located, let's say, then the derivative would tell you how fast its location is changing. In other words, its velocity or maybe its speed. Okay, well, we saw that way back in the first chapter when we first started talking about derivatives. So what would it mean to take a second derivative? Well, of course, there's a notation for it, right? So we're going to take the derivative of the derivative. So we put two little primes, and when you read that, you read it as f double prime of x. And, same derivative rules, so we take the derivative a second time, and we get 12x minus 8. You think, okay, well, if the first derivative represents velocity, how fast something is changing location, then what would its second derivative be? Well, I suppose you could say it's the rate of change of the rate of change. Or you might think it's how fast is the velocity changing. And well, how fast is velocity changing? That's acceleration. So if you're accelerating, then you're typically think of acceleration as you're getting faster, right? You're getting faster, so your velocity is changing in the positive direction. But you might also be slowing down. That is deceleration. Same idea. Okay, so what are we going to do here in this section in this chapter? Well, it's all about graphs. So let's look at how the second derivative, what would that look like in a graph? And so we need to define, let me just go ahead and show you both of these. So we'll define concave up and concave down, and they are these shapes. If your graph is curving upwards, it makes this U shape, then we're going to say that you are concave up. The graph is concave up. Well, that happens to be when the second derivative is positive. We might have the opposite, concave down, when our graph is curving downwards. It's making that sort of shape. Well, that's going to match when the second derivative is negative. And I didn't want to go into why, all the details of why this would imply the second derivative is positive and why that would mean the second derivative is negative. It wouldn't take that long, not anything that would be above us. Maybe if we were in class, I'd say, hey, you guys really want to know why? But I didn't leave this as part of the lecture. If you want to know about that, certainly come and ask it in the Zoom session. Okay. Really close connection to increasing and decreasing, right? If you're increasing, then your first derivative is positive. If you're decreasing, your first derivative is negative. And then the concave up, concave down kind of matches with the positive, negative, but now second derivative. Okay. A lot of things we do in this 4.2, they're actually going to feel exactly like what we did in 4.1 with increasing and decreasing. Now we're just working with the second derivative instead of the first derivative. So there's going to be a test, kind of like we had an increasing, decreasing test. Okay, well, I'm getting ahead of myself. We need to define the equivalent of the local max or local min. it's called the inflection point. So I'll show you a graph of what this looks like also, but an inflection point is where the concavity changes. And either way, so if the concavity goes from positive to negative or negative to positive, we just call them all by the same name. They're all inflection points. Okay, so again, that's like the corresponding piece to the local max and min when we change increasing, decreasing. All right, I want to show you all these in one example graph. This is a similar graph to the way we started off 4.1, but now we'll look at other attributes of that curve. So, I've kind of drawn just any kind of generic curve, sort of making that shape. And then I wanted to point out that one spot there. And okay, let's chat about this. So here, this f of x would be concave up from 4 to infinity. So at that moment, it starts to curve upward. So it's going downwards for a moment, but it's curving back up. In a similar way, this f of x is concave down from negative infinity to 4. So we've got that downwards curve right there until we hit 4. And so what does that make the point? That's our inflection point. That's where it changes. And so it's got this, you can see where it gets the name, right? It's like it's curving this way, and then it sort of like pops and starts, kind of flips inside out or something. It kind of like goes back the other direction. It's kind of the way it feels to me. Okay, so yeah. Okay, well, I think at this point, oh yeah, we need a test. Oh, I thought we were diving into examples. No, we've got the concavity test, and we probably maybe have a good idea of how this is going to work if you remember the increasing decreasing test. There's 2 steps, and they feel very, very similar to the increasing decreasing test. We're going to find the x values where the second derivative is 0 and where the second derivative does not exist. And step 2, we are then going to mark those x values that we just found on a domain line, like a number line, and test each interval, but this time we're going to test in f double prime of x. So if you remember in 4.1, the first step to the increasing decreasing test was to find the critical values, the critical numbers. Well, that is the same idea, just with the first derivative, right? Where does it equal 0 and not exist? And then you mark those on a line and test each interval in the first derivative. It's exactly the same test for concavity, except we use the second derivative instead of the first derivative. So kind of interesting that it works out that way. Okay, now we are ready for our first example, and these questions usually aren't short because there's several steps to them and a lot of plugging numbers in and number crunching, but it is what it is. So let's go for it. Our first example, we're going to be asked, let me keep all that on the screen. We're going to be asked to determine the intervals of concavity and any inflection points. And let's start off with this one. F of x equals negative x to the third plus 3x plus 5. That's actually the same function. We did an example in 4.1 with this function, so it'll serve us well here also. Okay, if we're going to find the intervals of concavity, of course, we need the second derivative. So here we go, and maybe I should actually keep that problem there, and then just kind of link them together. Oh, okay, something like that. All right, so we've got the first derivative, so we'll take the first derivative. F prime of x equals negative 3x squared plus 3, but we only do that so that we can again then find the second derivative, and fortunately they're getting simpler every time. The second derivative, f double prime of x equals negative 6x. Okay, so we're going to take a look at when that second derivative equals 0, and are there any x values when their second derivative does not exist. I'm just going to show you guys this side by side. And this for this particular function, these won't take long, right? We've got, okay, set it equal to 0. Well, that's going to be pretty fast to solve. And maybe at the same time, does the second derivative ever not exist? Well, we're thinking like, do we ever divide by 0? That sort of thing. And no, that's not going to happen for that function. Then of course we can just go ahead and solve. So those are that finishes the first step. Okay, so then second step said, all right, whatever you get for answers here, and we just have the 1, x equals 0, plot that on a domain line. Well, our domain for this function is negative infinity to infinity. So I've just gone ahead and drawn the entire number line. And I only need to mark that one location there for my one solution to where the second derivative equaled 0. So I'll mark 0. And we can tell that this has cut the domain into these two intervals, and it just so happens to be the negative numbers and the positive numbers. And if you remember how this worked in 4.1, same idea, just with the second derivative. We're going to pick one value to represent this interval. We're going to pick another value to represent this interval. We're going to plug them in to the second derivative and see what happens. Okay, so I kept it easy. I chose x equals negative 1 to represent the first interval. So I'll put that into the second derivative, which the second derivative was, well, it was just negative 6x, right? So plugging in negative 1 gives me positive 6. And just like before in the other test, I don't care the number itself, just the fact that it's positive. So then I'm going to go back and put a big plus sign right there. Okay. Then for the next interval, I pick any positive number here, anything bigger than 0. Well, how about positive 1? I will put that into the second derivative, and I get negative 6. Again, I don't care that it's negative 6, I just care that it's negative, so I'm going to put a big negative sign right there. And with that, I'm able to answer the first part of the question, where is it concave up and concave down? This function f of x will be concave up where I get the plus sign, concave down where I've got the minus sign. So concave at negative infinity to 0, concave down 0 to infinity. Okay, now this question did have a second part. It was to determine any inflection points. So I can tell by looking at my chart back here that 0 is an inflection point because the concavity changed, right? So I need to find the y value. Concavity changes at x equals 0. Okay. I'll just show you guys the rest of this. So I'm going to take the 0. I need to find the y value. I want the full point, not just the x value. So I take the 0 and I plug it back into the original function f, which was negative x to the third plus 3x plus 5. So plugging 0 in, well, that's nice. f of 0 equals 5. So my inflection point is the point 0, 5. And that finishes the question. If we were in class, what I would do at this point is go back and graph on Desmos that original function. You might type in y equals negative x to the third plus 3x plus 5, and just take a look at it and see if it really is concave up from negative infinity to 0, and then it'll have an inflection, go concave down from 0 to infinity, and right there at the middle, at the point 0, 5, it's got the inflection. So it's going to do something like, kind of curve up and then start to kind of, I'm not sure exactly what it does, but it'll kind of do something like this, maybe. That'll be right there at 5. Concave up, hit 5, go concave down. Check it out. Okay, I'm going to conclude this video here. We'll do a more difficult example in the next one.